All right, welcome back to PyCSE. Today we have a new video on CAN networks. And last time I talked about a sklearn compatible implementation I made in PyCSE that had DPOSE, the deep propagation of shallow ensembles. And today I'm going to talk about a second implementation that uses the LLPR, this last layer prediction rigidity, that was recently published by in this paper. And you'll see up here the standard deviation is related to something called the delta method on sort of the last layer features. And so you can kind of think of everything up to the last layer being some fixed nonlinear transform, and then from there it is a regular linearized propagation of uncertainty that follows this formula. And so this formula is basically the delta method. This FTF is an approximate inverse Hessian or Hessian covariance matrix, inverse Fisher matrix, etc. There's a regularization parameter here that just makes sure this thing is actually invertible. And then these are sensitivities to, or this is like a sensitivity, and then this is how the last layer depends. So I asked Claude to just implement the LLPR mostly to see if it could, and then to see what it would do afterwards. So this has some advantages over the ensemble method. Number one, we don't change the architecture at all. There's no ensemble. You just have the model and you work out these parameters up here after you do the training. Now the capital FTF does depend on the train set, but you calculate it one time and store it. And so this prevents you from needing the full Hessian of the full network, which in a large model would be impractically large. This is instead just the partial Hessian of the last layer. So that makes it quite a bit smaller. And then after that, this is all linear algebra, so it's pretty fast. Okay, so this got implemented here. Again, I use JAX, and so I'm just going to walk through and show you how it works. So here's going to be the same kind of test set we made before. It's not complicated. It looks like this. And then to fit it, we create our model here, KANLLPR. We have to choose how many layers, the grid size, that's the number of, kind of the number of knots in the different activations on each edge. And then we just call fit, and then we get a report here. And the report tells us about the architecture, this spline order, cubic. We use this optimizer. With BFGS, sometimes you'll see converged equals false. That's because it uses a tolerance that it may not have gotten to within 300 iterations. But you can look at the loss and other features to see if it's actually good, even though it's technically not converged. Then we predict with uncertainty here, and so this is the plot that you see, and we have a very good fit to this data, not surprising based on the last one, and you see pretty good confidence intervals. Now, the LLPR has to be calibrated, and that was sort of hidden in the alpha squared. I didn't talk about it a whole lot. In the paper that we wrote on the delta method, this is usually something like the mean squared error that's done. And then zeta squared here is again just a regularization term. In our earlier paper, we looked at the eigenvalues and then used the smallest eigenvalue to make sure that that matrix was invertible. Here we use it as a fittable parameter. So when you see zeta values that are very large, that means that you basically don't know enough about it because you are making a very large number to make that matrix invertible. And we can see various calibration diagnostics here. You want this number to be ideally 0, this number to be ideally 1, and this number to be very low. These indicate a well-calibrated model. We can also look at these metrics. Now, this is the LLPR has a lot of advantages. I said mostly we don't need an ensemble, but a consequence of this is that we can't really do heteroskedastic noise very well. So here you see we have heteroskedastic noise that gets bigger and bigger, and it does okay down here, but it doesn't do as well out here, and there's really no way around that because we have just a single, we assume that there is a single noise across the whole range. So if you have heteroskedastic noise, the ensemble is going to be better, but if you don't, then it is nice to have this simpler, faster method. Let's see, this supports separate calibrations for multiple outputs, and so that makes sense. If you have a multiple output, you may have bigger errors in one output than another, and here we just kind of demonstrate how you make the fit. You get different alphas for each one, and you get different calibration values for these as well. And so that's kind of nice if you have multiple outputs. And here is evidence of that. Here's a low noise output channel and a higher noise output channel that just kind of does the right thing. Now note it's kind of jagged, and I think that's because this depends on the features at the point, and those are changing kind of through here. Okay, I put in a comparison here. This is the original CAN. And then we have the KANLLPR. Let's see what we get. The KANLLPR is faster to train. That's because we don't have the ensemble. And it is, both of these seem like they're pretty well calibrated. If you look, you know, the predictions are roughly the same. Accuracies are about the same. And so finally you have, you know, this little table. This is all in the LLPR demo up here that I'll put in the video description. You can kind of get some ideas of what the comparisons are. And you can specify these manually if you want. We have some regularization options. And then down here you'll just see some information about using the KANLLPR. All right, so that summarizes today's video, just to illustrate that we have, it's really like a golden era for uncertainty quantification in some ways. We have more methods to choose from than ever before. It still is a challenge to know which one to use and when to use it, what the limitations are. We don't always know in advance if we have homoskedastic or heteroskedastic noise, but we have more and more options that are easy to learn, easy to use, and test out ideas with these sklearn-compatible versions. All right, that's it. Thanks. See you next time.